In this video, we will continue exploring conversion between vector and raster data, often needed when preparing data for modeling or when creating output maps. We have created a raster representation of schools, specifically schools' capacity, in the previous step. Let us now create a raster representation of streets with the variable speed limit. We will need that layer in future assignment. So instead of using 200-meter resolution grid cells, we will now use 30-meter resolution grid cells because 200-meter resolution grid cells would merge some of our streets together. So we will use g.region to set our resolution to 30 meters, and we will keep the same spatial extent. And now we will again use the command or tool v2rast to convert the lines representing streets to a raster map that will represent speed limit. And we will select the variable speed to use in the raster as a raster value in our raster representation. So now you can see that we again have the streets, but now the streets are colored based on the speed limit, and they are represented as 30-meter resolution raster. And you can zoom in, you can explore, you can see how that representation looks like. So we already have the streets speed 30 meters displayed, so we don't need to run the command drast, but let's add a legend so we can get rid of this one. And we will talk more about the legends later on. How to resize them, how to design their proper size, proper orientation, how to move them around and things like that. So I will put it here for now. So now we can use the out file to save the map represented in the display, or we can use the save button. And you can name it differently, something more meaningful than vector-rast. So we have converted discrete vector data to raster representation. Now let's run conversion from raster to vector data. And for the next example, we will take the streams derived from digital elevation model and represent it as a raster, and we will convert it to vector representation. So let's just use command line for this, just to run it more efficiently. So we will remove the current layers. And we should also remove this legend. And we will set our region to streams derived map layer with which we will be working. And you can see it is 10-meter resolution raster. And we can display it, so we can either double click on it here, or we can add it through here. or we can just run this command. And you may get it in a yellow color. I have changed the color table on this raster. But in any way, you will be getting, depending on the resolution of your screen, you will be getting this discontinuous representation. And we will be talking about why this raster representation looks like this. When you zoom in, you will see that it is actually a nice continuous representation. There are few spots where the segments were still missing, but as you zoom in, you can see that it's really nice and continuous. So we will discuss what the issue is here, but for now, to visualize it in a better way, we will convert it to vector data. So let's click on Zoom to computational region to get back. And let me switch to mouse pointer. And let's first thin this raster stream representation. And you have a question, explain why we are using r.thin module. So please read the manual page and try to explain why before we are converting this raster layer to vector lines, why do we need to run the thinning algorithm? So now we have a thinned data layer. You can hardly see it here. It is now with that yellow color. We can change the color table. Do you see with this set color table so that we can see them a little bit better? And again, this is something that we will be doing next week. So under define, we can use water color table and we will see them a little bit better. But you can see it's when you are zoomed out at the full computational region, they look discontinuous. Again, next week we will explain why. So let's convert them to vector representation, running the tool R2Vect. And now you can see that it has reconstructed it very nicely, and we have a proper vector representation. So we can change the color to blue with just simply running this command. And then we will just visually compare this layer, like the streams that are derived from a raster digital elevation that we converted from raster to vector representation, with the vector representation of streams that were digitized from high resolution orthophotos, and they are displayed in red color. So please now look at these two map layers and include some comments in your report about where do you see the differences. And when we will be doing flow routing, then we will try to extract our own layer from the digital elevation model, and we will be tweaking some parameters to make them look closer to what was digitized from orthophotos. And we will also learn that sometimes the streams digitized from orthophotos are less accurate and have less detail than the streams that are derived from high-resolution LiDAR-based digital elevation model. Okay, So now we can save this file. And let me, because I have here for the legend, I have here the streams derived twice. Okay, so let's just keep just one layer. And we can again save this map for our report using either this command or the save button. Okay. So, and the last step that we will be doing, last conversion, will be converting raster areas representing basins to vector polygons. When we are extracting streams from the digital elevation models, at the same time, we can also extract watershed boundaries. And the watersheds are then represented again as raster areas. So it would be like a discrete raster. And that's not very practical for many, usually like for display and for some analysis, it is useful to have the watershed boundaries represented as vector polygons. So let's now do that. Again, we will be using the command line just to go through it efficiently. So we can remove the previous layers. And we will set our region to the raster that we will be working with. And that's the basin 50K. And you can see that it's essentially the same region and same resolution as we had previously. So it wasn't really necessary to do that. But it is sometimes useful when you are not sure how that raster, whether that raster is exactly the same spatial extent or is it exactly the same resolution. Because what will happen, you will have behind the scenes resampling happening. So just to make sure that the conversion is done exactly on that original raster, it's good to set the region to that raster. Now we will convert that raster to vector data. Again, open that R2Vect manual page so that you know what these flags minus S minus V mean, and that we are now defining the type as area, while before we had type line. And I intentionally left here, created this basin 50K vector data previously so that I can show you what happens and how to deal with the situation where you already have when you already have that map layer. And that happens quite often if you make some mistake, you already generated, you want to correct that mistake, and then you will get this error that raster layer or vector layer already exists. So what you want to do, you want to overwrite it, and you use minus minus O flag. So I can use my arrow keys to recall that command, and then I will do minus minus O, and now it is rerunning it and displaying the result. Now this doesn't look that great because it is filling in those areas. So what we really want to have is let's look at the original raster. Then we will look at the basin data only the boundaries, and we will add the streams to see whether these derived basin boundaries or watershed boundaries fit with the stream distribution. So let's just remove what we have there because we will be creating a new representation. So this is that basin map that we have used as raster representation of watersheds. This is the result of these black lines are the boundaries of the polygons that were converted. And we can now switch off the original raster that I wanted to show you, and let's add those streams. So you can look at the boundaries and see that these are really divides or ridges, and that the streams go away essentially from these boundaries. And we will, again, this is a topic that we will cover in topic 7. So now we can save those basins. Map, and you should have all those maps in your current working directory.